Okay, so this is our second and final podcast of Unit 3, where we're going to talk about the last few trends that we need to learn about before our test. So this is going to cover pages 5 and 6, although it's really just kind of 2 trends, and you'll kind of see this even though it's 3. Yeah, we'll get to that. So, first off, electron affinity, there at the top of page 5. What is it? It is a measure of the energy released when an atom gains an electron. So think of when a person receives a gift. They release some of their gratitude and their energy, saying, "Oh, thank you, I love it so much." And you can almost kind of tell how much they love it based on how much energy they put into their gratitude and how much kind of energy they release when receiving that present. And the same thing is true with atoms when they receive an electron. That's supposed to make them more stable, more happy, and they will show that by releasing that energy. So the atoms that like and appreciate receiving that electron the most will release the most energy. So a simpler definition, kind of an alternative definition, I suppose, is how much an atom wants to add another electron into its orbitals. Now, we are going to take a brief moment for you to kind of write this down. This isn't something I'm going to test you over, but I just want to show you what this would look like in a chemical equation type form, where we have our neutral element adding an electron to it. That will mean that it is going to become negatively charged. And this energy term is on the product side after the arrow, meaning it's coming out when that electron is going into the atom and becoming part of the atom. Now, what I was saying earlier is that this is really kind of just 2 trends in this podcast, even though the title has 3, and that's because the trend for electron affinity happens to match exactly the trend for electronegativity. So the pattern is the same. The element that has the greatest electronegativity also has the greatest electron affinity, which is why we're going to jump into electronegativity right after this. But everything we say about the patterns for electronegativity are going to be true about electron affinity as well. And this should make it easier for you to remember these, because even though we've got a lot of different trends with a lot of different elements, both of these electron trends, the words that start with electrons in these trends, are both going to have the same pattern, the same greatest element. So let's talk about electronegativity. Below that periodic table, let's fill in our definition. What is it? Because it is different than electron affinity, even though their patterns and their trends will be the same. Electronegativity is a measure of an atom's attraction for electrons, specifically in a chemical bond. So this is kind of like a tug of war on the electrons, and we're going to learn a lot more about bonds in the next couple of units. But electrons are shared between atoms in a covalent bond specifically, but they're not always shared equally. So whoever has a higher electronegativity in that bond is going to pull harder on the electrons, and they're going to have those electrons for more of the time than the other ones. So they don't necessarily share perfectly equally, just like siblings. So how can we see this electronegativity thing change on the periodic table? Well, if we think about the nuclear charge, remember that this is what's changing and increasing as we move from left to right in any row of the periodic table. Well, as we have a greater and greater nuclear charge pulling harder and harder on that same energy level of electrons, well, then that means that our atom is literally pulling harder, has a greater attraction for the electrons around it, including when it is in a chemical bond, which means that electronegativity is going to be increasing as our nuclear charge increases. So, larger electronegativity as we get to the end of a row. Now, shielding effect, as we move down a column, remember that shielding effect, the more energy levels we have, then the more shielding the electrons on the outside of our atom have from the pull of the nucleus, which means they're less attracted to the nucleus, less firmly held in a chemical bond or otherwise, which means as we go down the periodic table, our electronegativity will decrease. Now, this is actually the same general pattern that we saw for ionization energy, but there's one key difference between the electron trends that we're seeing here and ionization energy, and that comes to the noble gases. The noble gases are at the far end of the periodic table, where we had said the electronegativity should be the greatest according to our nuclear charge. But remember that our noble gases don't form bonds. They don't want to gain or lose electrons and form a bond with another atom. So they literally have no electronegativity because they have no bonds to hog and pull on electrons in, which also means they have zero electron affinity. They have zero attraction or desire to pull on they don't release any energy when you try and give them an electron because they won't take it. So those noble gases have no electronegativity, which means that helium, which was our greatest element for ionization energy, is out of the picture for our electron trends. So let's go ahead and put all of this information, I'll summarize all of these words on that periodic table up above. Now, I just used this outline of the periodic table because all of the information that is on that other periodic table is a little bit busy. It's just important that we kind of keep an eye on where things are in general across the periodic table. So just did this to simplify things. So as we're going left to right, we said that our electronegativity and electron affinity would be increasing. So we're going to draw an arrow towards the right, but because those noble gases have no electron affinity or electronegativity, we're going to cross those out. They have none. Then up to down, we said that it decreases as we go down with the more shielding, so our highest electron affinity and electronegativity is at the top. And we put those arrows together, like I said, it would be pointing to helium, just like our ionization energy trend was. But with helium out of the picture, the highest electron affinity and electronegativity is going to be fluorine. So F has our larger electron trends. Now, if we do a couple of examples here, if I want to arrange these elements in increasing electronegativity, these get a little bit complicated because normally we would just go from left to right or right to left if these elements are all in the same column. But anytime we have a noble gas, that one is automatically zero. That one is automatically the lowest, but then fluorine is the highest. So we're going to have to start this with neon if we are going increasing. Remember, we're going to go from small to big. So starting from the smallest, neon, and then from the farthest away from fluorine to the closest gives us sodium next, and then boron, then oxygen, and fluorine last, of course, because it is the largest on the whole periodic table. So it has this weird kind of loop-de-loop kind of action going on, but it's only if a noble gas is involved in one of these electron trends. So our next set of elements highlighted here has the same kind of thing happening. We have a noble gas, which means that is automatically the lowest. Then we're going to go from farthest away to closest to our elements. And there we go. And then finally, we have these next few elements. And no noble gases involved means no weird loop-de-loops. So smallest to biggest is literally just going to be farthest away to closest. So Bi, Sb, Es, P, and then N. So not too bad. And if it had asked about increasing electron affinity, our answers would be exactly the same. Now let's talk about reactivity. You probably already kind of understand what this is. And reactivity is the ability of an atom to react or undergo a chemical reaction. And the most reactive elements, we've already seen this and talked about this when we talked about our special groups. The most reactive elements are at the edges of the periodic table, the ones that are closest to noble gases, because they're the ones closest to becoming noble gases electronically. They're going to get more and more aggressive at getting or losing the electrons that they need, the closer they are to getting what they want. Now, in general, what we said before, that our most reactive metals were our alkali metal group, and our most reactive nonmetals were the halogens, because of course the noble gases have no reactivity. And we do kind of have to talk about our metals and our nonmetals differently. This isn't all one trend, one pattern. It's based on how easy our atoms gain or lose electrons individually. So we're actually going to cross out these nuclear charge and shielding effect trend kind of placeholders here, right? Metals and nonmetals, because that's really what we need to be focused on here. So for metals, remember these are at the left of the staircase and nonmetals are at the right. Metals are going to react by losing electrons, aka, and our nonmetals react by gaining electrons. Because metals are losing electrons, that's what we called ionizing, becoming an ion by losing an electron, pulling one off. That's what we're calling it. Then the ionization energy trend is going to determine how easy it is for metals to react. And because our ionization energy decreases as we move down a group, the most reactive metals are going to be at the bottom of the periodic table. And then, of course, our nonmetals gain one or more electrons. Well, that's measured by electron affinity, how happy our atoms are at gaining an electron. So because electron affinity decreases as we move down a group, the most reactive nonmetals are going to be at the top of the periodic table. So these are completely opposite trends, even though we're talking about in both cases a vertical kind of shielding effect trend that's being caused here. So let's go summarize this on that periodic table up above. And since this does come down to our metals versus nonmetals, go ahead and emphasize that staircase in our periodic table once again. And then over here on our nonmetal side, of course, cross out the noble gases because they have no reactivity. And then our metals, like we said, are more reactive as we get towards those alkali metals. Nonmetals more reactive as we go towards the halogens, just automatically. And then we said metals get more reactive at the bottom of the group, and nonmetals get more reactive at the top of the group. So that means that francium is our most reactive metal, and fluorine is our most reactive nonmetal. And these are elements we've seen before. It's the greatest element of one of their trends. So now we just have to also remember that they are respectively their most reactive of our metals and nonmetals. So in these questions down below, we actually didn't do a very good job of making sure that you're comparing metals with other metals and nonmetals with other nonmetals. So we're going to real quick edit these first two because those are comparing metals to nonmetals, and we can't really do that. They're not quite equal and comparable. So if we are comparing rubidium and scandium, which one is going to be more reactive? Well, since they're metals, whichever one is closer to francium is more reactive. So that would be rubidium. Gold and niobium is also metals, so closer to francium, it means more reactive, and that is going to be niobidium. And then oxygen and sulfur are nonmetals, which means we're comparing them to fluorine, and oxygen is closer to fluorine, so it's the more reactive of these nonmetals. And that's quite literally all of the notes that we're going to be taking over this unit. That's all of the stuff we need to learn about these trends, these patterns in the periodic table. All that's left to do is practice them. Remember, we're going to be testing over this after we come back from fall break. So it's important that you keep practicing these ideas to be ready for that test.